Hello, advanced physics students. This is Dr. Brenzy here, and I had a request through Edmodo to show you guys how to do problems 5, 7, and 9 in lesson 2.1.1. So let's start off with problem number 5 here. So our problem says here that a small plane accelerates down the runway at 7.2 meters per second squared. And it says if its propeller provides an 11 kilonewton force, what is the plane's mass? So, what would that look like here? So let's go ahead and write down Newton's second law, which says that force equals mass times acceleration. And of course, our force is 11 kilonewtons, so 11 kilonewtons is equal to 11,000 newtons, so let's write 11,000 equals our mass. We don't know what that is, we're trying to find that, times the acceleration, and it says that the acceleration is 7.2 meters per second squared. And then I solve for mass by dividing both sides by 7.2. Pick another color here, just to make the steps a little clearer while you're watching this. So when I do that, I get a mass equal to 11,000 divided by 7.2, and that's going to come out to somewhere around, well, actually, let me go ahead and just pull out my calculator here. 11,000 divided by 7.2, and I come up with, now my calculator says 1,527.7 repeating, but if I want to express it in the correct number of significant digits, both of my force and my acceleration have 2 sig figs, so I'm just going to simply say that this is 1,500 kilograms. Okay, so that's the answer for part A. Part B, it says if the propeller provides twice the amount of force to the same plane, what happens to the plane's acceleration? Alright, well, if this variable f were to become twice as much, and I have the same mass, well, actually, let me back that up. Okay. We know that force equals mass times acceleration, right? Okay. Now, if I were to make this number, the force, twice as much as it currently is, so if I double this, in order to keep this equation balanced, I also have to double either the mass or the acceleration, or well, there are other possibilities, but it does tell us that it's the same plane, so that same plane has to have the same mass. So if I know the mass is going to be the same, that means that if I want to keep this equation balanced, I better provide twice the acceleration, or get twice the acceleration out. So if I double the force, it means I have to double the acceleration if the plane is the same plane. All right? So that is your answer to part B. Let's go into number 7 here. It says your friend can barely lift 35 kilogram concrete block on Earth. How massive a block could she lift on the moon? Acceleration due to gravity on the moon is 1.6 meters per second squared. Okay. Now, you're being able to lift a block means that you're able to exert more force than the force due to gravity. So if you think this as a free body diagram, and we learned about free body diagrams in the second lesson, her pull, the force that she can pull, has to overcome the force due to gravity. If it doesn't, then the force of gravity wins, and our net force is going to keep the block on the ground. So she's going to have just enough force to overcome the force of gravity. So let's figure out what the force of gravity is. So the force of gravity is equal to its mass, the mass of the block, times the acceleration due to gravity. So the force due to gravity is equal to our mass, which is 35 kilograms, times the acceleration due to gravity, and we know that is negative 9.8 meters per second squared. So if I multiply 35 times negative 9.8, I get something around negative 350 newtons. So if she is going to overcome this force, then her pull force has to be at least 350 newtons. And since she can barely lift that 35 kilogram concrete block, let's assume that the maximum force that she can exert is about 350 newtons in the upward direction. Okay, now let's go to the moon. Let's bring her onto the moon. And we know that her pull force has to be able to overcome the force due to gravity. Okay, so let's set up another equation with Newton's second law. So we know that this pull force is equal to 350 newtons. Okay, so let's see how massive a block she can lift on the moon. Well, we know that the force due to gravity for a block that she can barely lift is going to equal negative 350 newtons. Okay, and that gravitational force is equal to the mass of the block times the acceleration due to gravity on the moon. So let's go ahead and plug in this number into Newton's second law. So this is negative 350 equals mass. We don't know the mass of a block on the moon that she can lift, or barely lift, excuse me. But we do know the acceleration due to gravity on the moon is 1.6 meters per second squared. And that is in the negative direction. It's downward. So we're going to put 1.6 there because we're on the moon now. And well, it's pretty simple to figure out figure out the mass from here. We just need to solve this equation for m. So we're going to divide both sides, and we get a mass equal to something around 225 kilograms. Let's find out. 350 divided by 1.6, 218. Okay, but if I want to keep accurate track of my significant figures, this has two significant figures, that has two significant figures, so my mass also needs to have two sig figs. So I would actually write this as 220 kilograms. Alright, so on the moon, she is able to barely lift, a mass of 220 kilograms. Alright, that's number 7. Let's work on to number 9 here. Or walk on to number 9, excuse me. Alright, so it says here 9. It says a ball is thrown straight up with a velocity of 30 meters per second. What will the velocity of the ball be at its maximum height? Okay, well, what do we know about velocity at maximum height? When something goes up, we know that eventually it slows down, and it eventually comes to a stop when it gets to its maximum height, and then it's going to turn around and start accelerating downward. Well, right here at the very top of its flight, it temporarily stops. So the velocity of the ball at a maximum height is going to be 0. So for part A, velocity is equal to 0 meters per second. Okay. Part B says, how high will the ball travel? Okay. Well, In order to figure out how high the ball will travel, I need to use a displacement equation. So let's go ahead and try that. Let's put in displacement. D equals D initial plus V initial times time plus 1/2 AT squared. And let's start filling this in with information that we know. We're going to assume that the ball is thrown straight up from a distance of 0. So we're going to call this 0 in our little coordinate system here. So we're going to call this 0 height down here at the bottom where we threw it up. The initial velocity, it says here, is 30 meters per second, so we're going to add plus 30. We don't know the time yet, so we're going to put t in there. Plus 1/2 times negative 9.8 times time squared. Okay. Now, do I know the distance that it traveled to reach maximum height? No, that's what I'm trying to figure out, right? Because it says how high will the ball travel. This is what I want to know. But I don't know the time that it spends to get up to that height, this maximum height up here. So I need to bring in my other equation, the velocity equation. So let's bring that in and see if we can use that to help us solve for time. So let's write down our velocity equation. V equals V initial plus AT. And let's plug in what we know. Do we know the velocity when the ball is at its maximum height? Well, yes, we do. We just figured it out in part A. It's 0. Okay. Do we know the initial velocity? Yeah, we know the initial velocity. It's 30 meters per second. Oh, my arrow is going crazy on me. 30 meters per second. So let's fill that in. And then we have plus acceleration due to gravity is negative 9.8 times the time. And we can solve that equation to find time. And we're going to get something on the order of 3 seconds. Now, you might be saying to yourself, well, let's go ahead and round this off to the number of sig figs that we want. But actually what we want to do is we want to hold off and do our rounding at the very end when we find this value here. So let's actually go ahead and solve this equation for t. So we have negative 30 divided by negative 9.8. And we're going to actually get 3.06 seconds. Okay. I'm going to keep those other figures, even though I should only have, I believe, 2 significant figures, maybe even 1 actually, because it's 30. And I'm going to wait until I find this distance before I do sig figs. So now I know the time that it took to get from 0 up to this height. Now I can plug in this time into my displacement equation to find out what the distance is. So let's go ahead and do that. And give a little, divide my space up a little here so I can stay at least somewhat organized. So let's see here. So D equals, we can ignore this 0 part, so I'm not going to even write it. I have 30 times t. So that's 30 times 3.06. And then we have to add, well, actually, why don't we go ahead and say 1/2 times negative 9.8 is negative 4.9. So let's go minus 4.9 times our time squared, which is 3.06 squared. All right, now I just need to evaluate this expression over here on the right. When I do that, I get, I think this is 91.8. Let's find that out. Double check, make sure my mental math is correct. So 30 times 3.06, 91.8. Awesome. All right, and let's figure out what the second factor is. 4.9 times 3.06 squared. And my calculator tells me that that is 45.9. Right. So I have 91.8 minus 45.9. And when I take the difference of those two, I get a height of 45.9. Right. Okay. So my height is 45.9 meters. All right. Well, actually, now that I think about it, that's not quite correct because I forgot to round to the correct number of sig figs. And since our velocity only has one sig fig, technically speaking, I should really round this up to 50 meters because that's only one significant figure in my velocity, so I can only have one sig fig in my displacement. Alright, and it says here, how long will the ball remain in the air? So for part C. Now for part C, we could actually do this one of two ways. We could do it the hard way, or we can use some of the work that we've already done. Well, one way is, I'll explain the hard way to do it first. The hard way would be to recognize that this is a displacement of 0 when it comes back to the ground. So you would have an equation similar to this, but you would know that your displacement is 0, so you'd plug in 0 here, and then you'd have a quadratic equation to solve for t. So that's one way to do it. The other way to do it is to recognize that since we are throwing it from the ground and it is coming back to the ground, well, whatever time it spent going up is also going to be the time it spends coming down. So all I need to do is take this time that I figured out. This is the time that it took to go up. If I double that, that's the time that it takes to come back down. So the total time it takes for the entire flight is this 2 times 3.06. Okay? When I do that, I am going to get 4.12, or 6.12, excuse me. 6.12, and if I round that off to the correct number of significant figures, it is going to be 6 seconds. All right. So that is part A, part B, and part C. Now, if you want to stick around to see if this gives us the same answer, I'm going to show that on another slide here. So let's see here. Let's go ahead and rewrite that equation. Distance equals our initial distance, which was 0, plus 30 times time minus 4.9 t squared. That's our displacement equation. And remember, when it goes up and falls back to the ground, our displacement when it lands is 0. Yeah, let's draw a better 0 there. 0 equals 30 times t minus 4.9 t squared. Okay, now in this particular case, before I start plugging things into a quadratic formula, I quickly recognize that both of these have a factor of t squared, so I'm going to go ahead and factor those out. I'm going to factor the t out, and what I'm left with is 30 minus 4.9t. Now, the only time that this would be a good method to use is when you have no constant factor over on this side. If we have a constant factor, then you can't use this. But since there's no constant factor on this side, we can go ahead and we can factor out a factor of t. All right. So I have 0 equals t times this expression 30 minus 4.9t. So I get two answers for a possible value of t. The first one is that t equals 0. Okay. Because 0, the reason I can say that t equals 0 is because if this is 0, then this times this will be 0, so the entire product will be 0. The other thing that I can say is that this thing in your parentheses equals 0. So I can say 30 minus 4.9t equals 0. Because if this expression is 0, then that times t also has to equal 0. So now I have an equation with t. It's linear in t, so there are no squares to deal with. And then I can simply just go ahead and solve for t and figure out what it needs to be. So let's quickly do that. Let's subtract 30 from both sides. Alright, and when I do that, I get negative 4.9t on this side of the equation. And I get negative 30 on that side. And now I'm going to divide both sides by negative 4.9 to get t by itself. And I come up with t equals 30 divided by 4.9. Hey, that sounds familiar. 30 divided by 4.9. And when I do that, I get 6.12 seconds. But let's remember that our initial velocity was given to us with one significant figure. So we have to say that our time has to be one significant figure, and that is going to be 6 seconds. Hey, that's the same time we came up with back here on the previous slide. Awesome. So they both work. Great. Physics is awesome. Physics is consistent with itself. Okay, good. So that's problems 5, 7, and 9. Hope you found this video helpful, and look forward to seeing you soon. Bye.